Hi everyone, so this is the Oxazolone synthesis lab, and it's more specifically part 1, okay? So we're going to be splitting this into 2 days, particularly because it is a time extensive lab, and you do have to synthesize another molecule before you can actually get to the desired product, okay? So overall, we're going to be using an aldehyde and this acid that I'm drawing currently. This acid is hippuric acid. We're not actually providing you with this compound. So that's what day 1 is going to be about. You're going to be synthesizing this particular compound, okay? And then we're going to be forming this oxazolone, which is right here. And this particular oxazolone is a chromophore type molecule, so it's active under certain wavelengths of light. That's mainly because of all the conjugation there, right? So you have like that phenyl ring and all the unsaturated bonds in that molecule, okay? So we're going to be splitting this into 2 parts, like I said. So this will be day 1, and then day 2 is actually forming the chromophore, okay? So how are we going to actually synthesize the hippuric acid, right? So we're going to accomplish this by using an acid chloride, such as benzoyl chloride that I'm drawing here, okay? And then we're going to react that with glycine, so this simple amino acid here. So if we expose both of these to sodium hydroxide, we get to this hippuric acid compound. Now this particular compound isn't going to be the actual acid. This is the sodium salt of it, so there is no proton on that carboxylic acid oxygen, okay? So it's sodium. So in order to get to the hippuric acid, we have to neutralize that with HCl, okay? So let's take a little look at the mechanism of how this particular reaction will work, okay? So if we have an acid chloride, right? And it has an electrophilic carbon and an electrophilic carbon because of the oxygen and chlorine, right? And we have glycine, which has a primary amine and a carboxylic acid, okay? So if we're exposing both of these to sodium hydroxide, you have to be kind of careful about like where the sodium hydroxide comes into play, because the pK of that carboxylic acid is 5, or around 5, right? And then primary amines tend to be around 35. Okay, so one of them is clearly more acidic, so the sodium hydroxide is going to favor deprotonating one of them, right? But thankfully, we can actually do this reaction because the lone pair on the nitrogen can act as a nucleophile. Okay, see, so we have like 2 different proton abstraction points, okay? So, like I said, so both of these have lone pairs on them, but the lone pair on nitrogen is going to actually do the nucleophilic attack of that electrophilic carbon, and that's going to push the electrons from the carbon-oxygen double bond up onto the oxygen. And so we'll get to this doubly charged intermediate, but overall it's a neutral molecule, okay? So we'll get to this intermediate that I'm drawing here. Okay, so if we push the electrons from the oxygen back down onto the carbon, we can actually force that chlorine off, and we'll regenerate the ketone and form the amide that we're after, okay? But that still leaves the positive charge on the nitrogen, and we still have to remove the proton from the carboxylic acid, right? So at this point, that's where the sodium hydroxide comes in, and it'll and since we don't really, let's see, so we tend to have a high concentration of sodium hydroxide and a relatively large amount of it. So essentially it's an excess. So we can do deprotonation at both of these sites. Okay, because now that we've now that nitrogen has a positive charge, that the acidity of those protons are significantly higher than what they were before. Okay, so a couple of things to note about this lab is that you need to use minimal solvent when you're doing the recrystallization. Okay, the lower your yields for this particular reaction, the harder time you're going to have for the next synthesis. Okay, so recrystallize using minimal solvent. That's where a lot of people tend to lose a lot of their product, is that they just add too much solvent and they can't recover the compound. Okay, and then another thing to note is that you need to use IR and melting point to verify that you have made your compound and that it is pure. So it is important that when you're doing like these multi-step syntheses that you have pure material going into the next step, because if you don't, then you tend to either make side products or the reaction just doesn't work, since there might be a propensity to do one reaction over another. Okay, so it's really important to have pure material going into this next step. Okay, so one other thing that you need to do is, before the end of this lab, is to submit your product for proton NMR. So that'll help you identify whether or not you actually made your product or if you still have starting material left over. Okay, so safety. So you are using some strong acids and bases. So the molarity of the sodium hydroxide, you're using 6 molar sodium hydroxide and 12 molar HCl. And so those are actually pretty strong. So try not to make a mess with those. And then the benzoyl chloride in itself is also corrosive. And it does tend to react a little bit violently with water. So try to be careful when handling that. All right?